Now my next topic is relation between the susceptibility and relative permeability. Already I have proved, I have discussed that relative permeability mu r is very greater than 1 for ferromagnetic material, mu r is only greater than 1 for paramagnetic material, and mu r is less than 1 for diamagnetic material. Now let us try to derive this relation susceptibility and AC relative permeability of the sample. Okay, for this we have suppose we have originally there is an external magnetic field, say H, external magnetic field H, this is H, and we know that number of lines of force per unit area in free space is mu 0 into H, or you can say B 0 by mu 0 is equal to H. Now if we place a sample at this region, we know what happened. This side get magnetized with the pole S and this side magnetized with the pole N. So there is a induced magnetic movement M, and as a whole what happened from S to N inside the material, some additional lines of force exist or produce due to this material when it due to this material magnetized by itself due to this external magnetic field, because this magnetic material become magnetized by the application of the external field. S pole induced here, N pole induced here, and inside the sample we know lines of force exist from S to N inside the sample. So some more lines of force produced. Originally there are some lines of force of due to external field, but now due to magnetization of the material itself there are few more lines of forces are there. This thing I have already drawn over here. This green color line are external this green color line are lines of force due to its own magnetization, okay, and this white color lines of force original magnetic field. Okay, the white color are lines of force due to original magnetic field, but that green color lines of force are due to the magnetic field lines of force due to its own magnetization, because the sample itself get magnetized by this external magnetic field. Okay, therefore we can say that total number of lines of force inside the sample now becomes B per unit area. So B by mu 0, this is now new lines of force. This is not H but H plus something, because initially the lines of force is H, initially the field strength is H, but now the field strength inside the sample increases. Okay, so lines of force also increases. So now B by mu 0 is H plus I. And what is I? I is intensity of magnetization, and that is again chi H. So H taking common outside, so 1 plus chi. So B is now mu 0 into H 1 plus chi. Okay, again I repeat, initially there is a magnetic field H, so lines of force B0 is mu 0 into H, or you can say we have lines of force B0. If you divide by mu 0, we get a magnetic field when the sample is not present at this point. Okay, now the sample is present, so number of lines of force increases, therefore B0 now changed to B, and when you divide that B divided by mu 0, we get new magnetic field at this point. Okay, and this new magnetic field at this point now becomes H plus I, because additional lines of force are there due to its own magnetization, and you can say this additional is developed due to I. Okay, so H plus I, this is our now total magnetic field strength inside the sample, H plus I, which can be calculated B when divided by mu 0. So H plus I. How I is developed? I is equal to chi H. I have already mentioned I is equal to chi H. Chi is the susceptibility of the sample. This is susceptibility. Okay, this is your susceptibility. So you can say I is equal to chi h, so h taking common, so h common 1 plus chi, so B is now become mu 0 into h into 1 plus chi. And what is B? B is mu into h, mu into h. Mu is the permeability of the sample, mu is the permeability of the sample, or you can say B mu 0 into h is B0 into 1 plus chi. So you can say that number of lines of force inside the sample now increases from B0. Now B is now greater than B0. Why? Because when we multiplied B0 into something, multiplied B0 by 1 plus chi, we get B. So when B0 is multiplied by 1 plus chi, we get B. So B is greater than B0. Okay. So B is equal to B0 into 1 plus chi. So initially lines of force in absence of the magnetic field, in absence of the sample is B0, but in presence of the sample is B. So B is equal to B is greater than B0. So B is equal to B0 into 1 plus chi. So B by B0, what is B by B0? B by B0 is 1 plus chi. Now what is B by B0? B by B0 is, this is lines of force inside the sample, and this is lines of force in absence of the sample. So this is the ratio of the lines of force, or you can say this is a relative permeability. We have discussed in my last video. B by B0 is mu r, relative permeability. Why? Because B is equal to mu h, and what is B0? B0 is equal to mu 0 into h. H cancels, so mu by mu 0, and mu by mu 0 is mu r. This is B by B0. Okay, so this is B by B0. B by B0 is mu r, so this is mu r. That's why chi is equal to mu r minus 1. Chi is equal to mu r minus 1. As I have already discussed that mu r is very greater than 1 for ferromagnetic material. That means for ferromagnetic material, chi is also very greater than 1. But for paramagnetic material, mu r is just greater than 1. So chi is just greater than 0 but less than 1. Okay, say for example, if mu r is equal to 1.12, then chi would be 1.12 minus 1, that is equal to 0.12. that is a very small amount. And for this is for paramagnetic material. Okay, paramagnetic material. And for diamagnetic material, we have already mu r is less than 1. That means number of lines of force inside the sample decreases when a sample is present in the field. Then mu r is less than 1, say 0.98, then you can say chi is equal to mu r minus 1, that means 0.98 minus 1, that is a negative value. So chi is negative for diamagnetic substance. What does it signify? It signifies that I is equal to some negative constant into h. That means I and h are antiparallel. That means for diamagnetic sample, if this is the sample and you apply it along this side magnetic field, then your magnetic moment will be oppositely directed. That means this side is N and this side is S. Okay, this side N, this side S. So oppositely directed. Okay, this is what means a diamagnetic material behave when it placed in the magnetic field. That means its magnetization induced in the opposite direction of the applied magnetic field. Okay, this is the relation. And one more thing is that this is the relation, and one more thing is that your susceptibility, one more thing, I is susceptibility, and it is proportional to h. That means more you applied magnetic field, more is the intensity. That is, more and more your sample become magnetized. That means more and more your atomic magnet get aligned along the magnetic field. Okay, this is the intensity. I is proportional to H. That means as you increase the value of H, your I increases. That means your magnetic moment get increases. That means more and more atomic magnet align themselves parallel to the field. But if you increase the temperature, then this alignment get disturbed. That means it may happen that some of the atomic magnet get wrongly oriented or get oppositely oriented due to temperature. That means your orientation get disturbed. That means your I reduced. That means your chi reduced, because I is equal to chi H. Chi is equal to I by H. So as I reduced for a particular value of H, due to increase of temperature, your atomic magnet get randomly oriented again, start randomly oriented. So your magnetic moment or intensity decreases. Magnetic moment or intensity of magnetization decreases because atomic magnet now becomes randomly oriented themselves. So that means your chi become decreases with the temperature. So chi actually inversely proportional to temperature. That means if you increase the temperature, your chi decreases, and chi is equal to C by T. This is called Kuri Law. And this law holds for paramagnetic material. Okay. Now for ferromagnetic material, above a particular temperature, say theta, for example 720 degrees centigrade for iron is a ferromagnetic material, but above 720 degrees centigrade, iron behave like a paramagnetic material. Iron behave, that ferromagnetic material behave like a paramagnetic material, and hence its susceptibility now equal to C by T minus theta. Since now above theta, ferro becomes para, so this susceptibility now inversely proportional to T minus theta. That means above theta, this para, that means your temperature should be measured above theta. That means your temperature, if it is your temperature is greater than 720 degrees centigrade, then your Fe becomes paramagnetic material. Then above 720, that means 730, 740, 760, 780, as you increases more and more, your susceptibility of that sample reduce follow this relation. This law is called Kuri wise law. Okay. So for paramagnetic material, your relation is that chi is equal to C by T. C is a constant, T is a temperature. This is in absolute temperature. This is in absolute scale. You have to measure the temperature in the absolute scale. But as for ferromagnetic material, this formula does not hold good. But above a particular temperature, for example say iron, above 720 degrees centigrade, your iron becomes paramagnetic material. That means your iron is generally your iron is a ferromagnetic material, but above 720 degrees centigrade, your iron becomes paramagnetic material. And now if you increase the temperature above 720, then your susceptibility decreases following this relation, and this relation is called Kuri law. This is all about your magnetic material and properties. You go through these all videos so that you can have some ideas. And also you one more thing, you have to go through the comparative studies between ferromagnetic material, paramagnetic material and diamagnetic material. Okay. Few already I have mentioned that for ferro mu r is very greater than 1, for paramagnetic mu r is just greater than 1, for dia mu r is less than 1. Susceptibility for ferro is very greater than 1, for para susceptibility is greater than 0 but less than 1, and this is negative but small value. And again example, ferromagnetic iron, cobalt, nickel. These examples, paramagnetic examples are paramagnetic examples are aluminum, oxygen, copper, aluminum, your oxygen, your copper. And your diamagnetic material examples are zinc, silver, gold, etc. So these are 3 examples. Also paramagnetic material have a Kuri temperature. It doesn't have Kuri temperature, it has a Kuri temperature, it doesn't have Kuri temperature. Ferromagnetic sample have a Kuri temperature, but it doesn't have Kuri temperature, it doesn't have Kuri temperature. Okay, this follows Kuri law, this follow Kuri wise law, this doesn't follow any law. Okay, so these are the 1, 2, 3, 4, 5. There are 5 points. You have to remember mark up this formula. These points. Okay, 1, 2, 3, 4, 5 points. Okay, so these are theoretical type questions. You have to understand these things and you have to mark up these things and try to watch my full video one by one. Okay, don't jump 1 to 3 or 3 to 5. Try to watch video one by one. Okay, then the sequence is maintained and you can understand the videos very okay. Then your concept would be clear. If you jump from one video to another video without maintain the sequence, then you'll be confused. Okay, thank you.